Okay, we're going to start the next unit of material here by talking about charge and Coulomb's law. So charge, we may ask ourselves what charge is, and charge is a fundamental property of matter. It's like mass, okay? If matter exists, it's made up of charged objects. If you think about the atomic level, you have protons and electrons, and then even within the protons and electrons, we have these things called quarks, which are charged. Not all objects, like the neutron, for example, doesn't have a net charge, but it's made out of charged objects. And charge acts for the electric force just like mass does for the gravitational force. Now, when we talk about charge, we're going to break it up into two types. We have positive and negative charge, and we're going to have a smallest unit of charge, which it turns out is going to be the charge of an electron. So for normal everyday matter, the smallest unit of charge that matter can carry is 1 electron's worth of charge. So if you think about, like in chemistry where you have ionization, you have a +1 or a -1 or whatever. That means +1 electron or -1 electron. We can't split the electron into halves or quarters or whatever and put it on there. So really charge matters because when you get down to the atomic level, all matter interacts due to electrical interaction. Whether we realize it or not, pushing, pulling, tension, forces, friction, all that, really at the atomic level, it's the electrical interaction of these things. So we are most familiar with the concept of the positive and the negative charges of the proton and the electron from chemistry class. They have the same magnitude of charge, but opposite signs, okay? So the quantity of charge in both cases is the same. Even though the objects are not the same size physically, they have the same amount of electrical charge, just opposite in sign. And we assign the concept of positive and negative to them. Now we have other charges like the quarks we mentioned and other more exotic particles that you might find in like in the Large Hadron Collider that also carry charge, and those can actually have fractional charges, but those are not something you're ever going to really experience unless you're a particle physicist. So when we talk about something being neutral, really what we're saying is it has a net charge of 0. It has protons and electrons in it, but it has a net charge that adds up to 0. So if something's neutral, that means it has exactly the same amount of positive charges and negative charges, like a neutral atom. Okay, and then we move electrons around to create positive and negative ions. So when we move charges around, if we have an isolated system, those charges have to go somewhere. Just like when we talked about mass, we have to have conservation of mass or conservation of energy. When you have a closed system, that charge has to stay constant. It can move from object to object, but it has to stay constant. So just like in chemistry where you have to balance the equations and make sure you account for all the charges, that's conservation of charge. That's the basis of the conservation of charge. Now, the reason this matters is that tells us how things will charge if we move charges from object to object. Okay, that tells us if we have, say, for example, we took 2 pieces of tape and stuck them together and we made sure that they were neutral. If we pull them apart, we're going to transfer charges. So if one becomes negative, the other one's going to have an equal amount of positive charge because we know that they started out neutral, so the system has to stay neutral, so they have to add up to 0. So the pluses and the minuses have to cancel out. Now, the way charge moves is we have to have electrons moving, okay? Normally the way charge flows is through electrons being transferred. Now, in some cases, like when we have hydrolysis, in water, for example, we can move positive ions, but the focus of our study is going to be just on moving electrons around. So there's different ways that you can charge objects. So one of those is by making direct contact. Like I said, we rub things together, we pull the tape apart, or we can create a charge by induction. And what that means is we bring something charged very close, but we don't touch. So there's not a direct transfer of charge there, okay? And this will work for both things that we identify as conductors, which are typically metals for electric charge. Conductors have bonds with their electrons that allow the electrons to dissociate from the atom and move freely through the bulk of the material, whereas insulators don't. They can still become charged, but they will not transfer the charge nearly as effectively as a conductor will. So what I'm going to do is I'm going to stop sharing my screen. I'm going to click on this sim here. I'm going to stop sharing my screen and try to show you this, but I remember last time where I messed up. So what I will do is I'm going to stop sharing and I'm going to share this new screen so that we can see what's going on. Okay, so hopefully this works. Okay, so let's see if this, and that should show up, I hope, because it's the same window. All right, so what we've got here is a sweater that is neutral because it's the same numbers as pluses and minuses, a balloon that is neutral, and a wall that is neutral. So what I'm going to do is I'm going to bring the balloon over and I'm going to actually touch the balloon to the sweater. So do that. And notice what happens because of the interaction of the two materials. The balloon gathers up a bunch of negative charges off the sweater. So I charge that balloon by literally touching it to the sweater. So that's charging by touch. Now, watch what happens when I bring the balloon over to the wall. The wall is neutral, but as I bring the balloon over, what's going to happen is those negatives in the wall are going to try to repel from the extra negatives on the balloon. Like charges repel. So negatives will repel negatives, positives will repel positives, okay? So the negative charges are not leaving, so technically the wall is still neutral, but what it does is it creates the effect of a little positive patch of charge there. Now, just like like charges repel, opposites will attract. So what will happen is this balloon, if I let it go, will stick to the wall because I've moved my mouse off of it. It sticks to the wall because the wall acts like it's got a little area of positive charge. So what I've done by bringing this charge close, I have induced an effective positive charge on this wall. I'm not actually touching the wall yet, so I've induced an effective positive charge on it, okay? Or if I bring it over here, it will be attracted to this sweater because the sweater is now positively charged and the balloon is negative. And because both of these things are insulators, the charges can't leave, they're stuck there. So the balloon is going to stay negatively charged until we discharge it physically somehow. Okay, so let me stop sharing this and I will share back to the PowerPoint. Hopefully that solved the problem of the last set of notes. Okay, so if I had had a conductor, what would have happened is the excess charges would have drained off. Like the balloon would have lost all of its charge if it was made out of metal instead. It would have drained off. Okay, so the law that governs how these things are attracted mathematically is called Coulomb's law, okay? Coulomb's law looks at the forces between two charges, so pairs of charges. If I have a lot of charges, I just add up all the pairs, okay? And this is where we have to go back and remember how we do vector addition from Physics 1. So if you don't remember that unit from Physics 1, go back and review how to do the component method of vector addition. So this force can be attractive or repulsive. It's a lot like gravity when we look at the formula, but gravity is always attractive. It's always trying to pull things together. Coulomb's law can attract or repel. It can push things apart or pull things together. So it's going to depend on whether you have opposites, which are going to attract, or likes, which are going to repel. So a positive and a negative will always attract each other. A positive and a positive will repel, and a negative will repel. Now, neutral things, because they can be charged by induction like the wall, will always attract both charges. So just because something's attractive to a charged object does not mean that that thing has the opposite charge. It could have it, but if it's also neutral, just like we saw in the little simulation, we can induce a charge on that thing that will become attractive to the object also, the charged object also. Now, Coulomb's law measures charge in a unit called the coulomb. A coulomb is a huge amount of charge, okay? The unit of charge for one electron is 1.6 times 10 to the negative 19 coulombs. So one electron has a tiny little amount of charge, and we put a negative sign on it because that's the charge of the electron. The proton will have 1.6 times 10 to the minus 19 coulombs also, but it would be a plus amount. So when we talk about Coulomb's law, we do just like we did with the gravitational law. We look at 2-point charges, Q1 and Q2, a distance apart, r, and we find the attraction or repulsion between them. Just like with the Newton's law of gravitation, we have a proportionality constant, except it's a whole lot bigger than the proportionality constant for the gravitational attraction law. So when we write down the formula, it looks a whole heck of a lot like Newton's law of gravitation. It's between the two bodies, so the force of 1 on 2 is equal to the force of 2 on 1. They just are in opposite directions. So it's a third law situation, just like we had with gravity. Now notice I've got magnitude signs here because I'm not going to worry about the negative sign on a charge. All that's going to do is tell me which way to draw my vector problem. And when we work problems on Wednesday, you'll see that. So I've got the magnitude of the charge of the first thing, the magnitude of the charge of the second thing, divided by the distance between them squared. So charge needs to be in coulombs, distance needs to be in meters. Then this proportionality constant is what brings the force up to the correct size. And if you remember in physics 1, the gravitational force was very small, so we had to have a small proportionality constant. The electric force is much, much stronger. The Coulomb's law force is a lot stronger. Think about like static cling, or when you have those little static window designs that you can put up there, or if you pull a piece of saran wrap off the roll and how it tries to wrap up on your fingers. That's all electrostatic force. That's what you're experiencing there. Now, the K constant is a number that depends on the different units we use. For us, we're going to use Newtons, meters, and coulombs. So that value is 8.99 times 10 to the 9th Newtons meters squared per coulomb squared. That works just like the one for the universal gravitational constant. It's a proportionality constant. So this is a constant, little k, that you just write down. It's related to the speed of light in the medium. So sometimes we will, instead of using K, we will replace that with 1 over the quantity 4 pi epsilon naught, where epsilon naught is something called the permittivity of free space. And that's how easy it is for electricity to move through that material. Okay. So it's the speed of light. It's related to the speed of light. We solve for the speed of light based upon the permittivity, and then when we get to magnetism, we'll see its cousin called the permeability. And those two things determine how fast light can pass through different materials. In this case, we're talking about free space or vacuum, basically, no material there. If I've got lots of charges, what I do is I have to do a vector sum. I have to do a component method vector addition of the charges. Usually I'm solving for the force on a single charge due to all of the rest of them. Now, if you were in the calculus-based class, eventually what we would do is turn this into an integral, and we would integrate over a shape to figure out the force, but we're not going to do that. We're just going to add up some stuff, and you'll see lots of examples of that when we work problems on Wednesday. So you use the component method, you take the x and the y components, you remember how to use Pythagorean theorem, all that good stuff to find the total force. Okay, so we have this idea of force, and it has to be caused by something. Just like weight, the force of gravity is caused by the gravitational field. So without the gravitational field, we wouldn't feel the effects of weight. Well, here, without something called the electric field, we would not experience a Coulomb's law of force. So the two things are related. There's a field causing a force. So it's like a chicken and an egg thing. You got to have a field to have the force. Fields, it's hard to explain what they are, but I can tell you where they are. They are, if you have a charged object, it has a field around it throughout space. Just like if you have a mass, it has a gravitational field around it. So any charge will have an electric field around it based upon the size and the sign of its charge. Okay, so the value will be determined by the magnitude of the charge and how far you are away from it, and the direction will be determined by the sign of the charge. Okay, and other charges will notice the field of this first charge and it will be affected by it. So that's what really causes the Coulomb's law situation. Okay, so I'm going to again stop sharing here real quick and we will look at another little demonstration. Okay, so let me share this screen. See the right thing? I think I'm getting this figured out where it will work. Okay, so for example, if I bring a positive charge out, okay, so these arrows indicate the direction of the field. You'll notice they're getting dimmer to show that they're getting weaker. Now, we assign the field direction for a positive charge to be outward. So like sun rays coming out. It would come out spherically in every direction, okay? So this would be the field of the positive charge. So let me get rid of that. Now I'll put in a negative charge. The negative charge, also the field gets weaker, but now notice the direction is opposite. It points in toward the charge, okay? So the thing about field values is field values have to be unique in space, okay? They can't be multi-valued at a particular point. So, for example, when I bring in a positive charge here, remember its field lines point outward. So what happens is, since the field from this positive charge here points to the right, and the field from this negative charge in here also points to the right, they actually link up. They're pointing in the same direction, so they add together. And then this is what causes that attractive force between opposite charges. It's because their field lines link up like this, and it's trying to draw those two charges together. Okay? Now, I can contrast that with two like charges. So let me just put two positive charges in here. Now, notice, first of all, in here, the field line in here points to the right. So let me bring in another positive charge and put it over here. Its field would try to point to the left. So here in the middle, they cancel each other out because they can't be multi-valued. They can't be pointing in opposite directions. Okay, so this is why like charges repel. If I put two negatives here, I would get the same kind of thing going on. So like charges repel and opposite charges attract. Okay, all right, so that we're going to stop right there, and I'll pick this up in a new recording.